as far as questions I know about. Has anyone got any questions before we get started today? And then we'll get working on our next section 5.2. Okay, so what we're going to look at is called the definite integral. It's not really that obvious what that is about. So essentially, the definite integral is the same thing as asking someone to find the exact value for the area under the curve. Yeah, we're still on areas under curve. And this section is going to be the end of what I would probably call the awkward or messy part. Once we get by this, things become, in my opinion at least, a lot cleaner because we use algebra to find exact areas under curves. So the definite integral is the exact value for the area under a curve. And we use three methods. First method, we've already seen. You can use your calculator. And that works. But in this section, we're going to use two other methods. One is you can use geometry. You can find the exact area under a curve using geometry, provided that the shape that you're trying to find the area under the curve is made up of rectangles, triangles, and parts of circles. And then the last one, and this is the killer. This is the one that if you talk to anyone who's ever done Calc 2, they will say, oh God, Riemann sums. They were horrible. That's the third method. I think we do 3 or 4 of those, and that's it. Now, once we have figured out using Riemann sums how to find the exact value for the area under the curve, right? Once we use it to find the definite integrals, what we do then is we say, hey, that was an awful lot of work. Isn't there a shortcut? Isn't there a nice quick way of finding area under a curve without having to do, 80 strips with the Simpson rule, or hit buttons in a calculator? We don't know what it's doing, but the calculator is figuring it out for us. Or hoping that the shape is just made up of rectangles and triangles and bits of circles. Or having to do this really messy thing called Riemann sums. Is there a better way to do it? And the good news is, yes, there is. And the process that you call finding antiderivatives is going to be the way forward. That's going to be the guy that's going to allow us to kind of forget about doing all this messy stuff. But we have one more day of messy stuff, so we might as well get used to it. So only for completeness, because there isn't any questions in number 1 using the calculator. But let's suppose I was being asked to integrate, right? Or find the area under the curve is another word for it, from 0 to 1 of x squared plus 1. Nothing too spectacular. We have done similar looking things, but if we had to do it using trapezoid rule with 10 strips or something, we'd be here all day doing it. So thankfully, we're not going to do that. I'm going to, in a few moments from now, there we go, I'm going to set up my, can't I see that? That's weird. Let me try something. I'm having some, I guess you'd call it technical issues. Right. Okay, open up my emulator. Looks like it should be visible. Why is it not? Oh, go figure, it's just being weird. So, here is my calculator. I'd like to get the exact area, excuse me, from 0 to 1 of x squared plus 1. So you go into y equals, you type in x squared plus 1. You go into the window and you start at 0 and you finish at 1. And then you go to this choice here. What's the fourth button from the left or second from the right? You go second, calculate. Option 7, which is finding area under curves, which are also called integrals. Choice number 7. Pretty boring curve. It's now asking me for the lower limit, which was 0. Press enter. The upper limit, which is 1. Press enter. And it fills it all up. And the answer I get is 1.3 repeater, which, if you know 0.33 repeater is a third, it's the same as 1 and a third, which is 4/3. So that's essentially how you would get the exact area under a curve if you wanted to use the calculator. Right? Plug it in, get your answer, make it look as exact as you can. So that's really just for completeness sake. Now the second one is going to be, how do we get an exact value for the area under a curve when the curve is made up of bits of these guys. So this is very visual, and I don't want to draw it on the paper here because it'll be a right mess. I'm just going to nip over to their pictures and show you, because they're much cleaner than I am. So here is an example of a shape. Right, a curve starts at 0, finishes over here. What's that from there to there? It's going up in 3s. Okay, so 21 to 27. So it goes at 0 and it finishes at 27. And down here, we're being asked to find various integrals. So for instance, I want to find the integral from 0 to 6. Well, here is 0 and here is 6. I wonder if I can make that a little bit bigger. I can. Okay. Now, vertical line at 0, vertical line at 6. The shape that we're trying to find the area for is this shape here. You see it? Now, the way my mind works is that there's a little rectangular piece at the bottom, which is what, 6 units long and 3 units up. So that's 6 times 3. So it might look something like this. 6 times 3. That would get me this piece here. And then there's a triangle at the top. And the triangle is a half base, which is 6, times height, which is 6. So I would then add 1/2 of base times height. So that's what my calculation would look like. So this piece, the rectangle at the bottom, is 18. And the triangle is also 18. So the correct answer would be 18 add 18, which is 36. And let's check it out. There, that's good. Now, suppose you want to get the area from 0 to 15. Well, you start at 0 and you finish here at 15. So what you have to do is you have to take this shape and break it into pieces. I already know the answer from 0 to 6, so why don't I save some time and split it at 6 and say this piece here on the left is already known, it's 36. Then I've got a little rectangle in the middle, which is 3 boxes, that's worth 3 and that's worth 9, so that's 27 for that guy. So what do I have? I have 36 for the piece on the left. The rectangle in the middle is 3 times 6, so that's 18. And then at the end here, I have 3, 6. That's 6 by 9. So it's a half times 6 by 9. So we go a half times 6 times 9. And I believe that gets you 27. So you would take all the different pieces, which is what, 36, 18, and I believe I said 27 for the third one. And you add those guys up and you get 15, 21, 2, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8. I hope the answer is 81. I'm about to find out. If it's not, it's just because I can't count. And I can't count. So let's figure out why I can't count. Right. The shape that we are trying to find. So I'm actually going to draw the damn thing. I think it's the only way to make sure that I can put all my boxes in and count them properly. Looks something like this. This scale here goes 3, 6, 9. Okay, that's as far as it goes that way. Then it goes 3 and 6. So our shape goes from here to here. Okay, that's good. And then 6 to 9 goes along with it. That finishes there. And then it goes to 15, I believe. So 12, 15. And then it goes down to here. So the one I got wrong was the integral from 0 to 15 of this function. So I'm splitting it into these 3 pieces. This piece here, we already know that its answer is 36, and it's been verified as 36. So it's going to be made up of 36. Plus, this piece here in the middle is 3 times 9, which is 27. I couldn't have screwed that up. And this guy here is a triangle. And its base is 6, and its height is 9. So it's 1/2 6 times 9. So that's going to be 36, 27, and then 27 again. And if we put all that together, let's see what we get according to my calculator. 36 plus 27 plus 27 more. I get 90. And there is my mistake. I think I didn't have 90 the first time. And I'm just going to type in 90 and check it. And I had originally 81 because I can't count. And it's correct. Now, the next integral that you're being asked to find starts at 15 and finishes at 21. I hope I've given myself enough room to do that. So the shape goes down 3 boxes. 1, 2, 3. Okay, makes it. And 21. So 18, 21's there. So basically it goes here. And the shape that we're trying to find the area from 15 to 21 is this little rectangle. A triangle, I should say. Well, triangles are half the base, which is 6, times the height, which is 369. And this is where we have to be a little bit tricky. I know that for your entire math career, for very good reasons. You've always been told areas are positive. You can't get minus 10 square feet, right? It doesn't make sense. That's now no longer the case, because we describe areas above curves or areas under curves by anything that's above is considered positive, but any curve that is below the x-axis, the answer you get is negative, which makes this guy not 27, but negative 27. And it is what it is, right? And there's good reasons why you would look at this in a slightly different way, because essentially the y values, which are part of the answer, are negative numbers. So you're really going 1/2 times 6 times -9, right? The calculation does involve you working with negative numbers, and therefore you would expect you might get negative answers. And if that doesn't work for your brain, anytime a piece of the curve is below the x-axis, that portion of the area is considered to be a negative amount. Now, suppose I ask you to find the area under the curve from 0 to 21, which is essentially starting here and finishing there. Now, if you've already got some of the answers, you should use that. From 0 to 15, I already know that answer. And then if I add the 15 to 21 part, then the combination of those two will represent this area. Now, the first guy is 90, and the second piece is negative 27. So the net effect of that area and this negative area is 63. So when we talk about the area under the curve, I don't want you to think of it as a physical area, which will make you think everything should be positive and everything should be added together. I want you to think of it more as a kind of mathematical thing where areas above the x-axis are positive things, but areas below the x-axis are negative things. And that when you get an area under a curve, it's a combination very often of positive pieces interacting with negative pieces. And so the full end result could easily be negative or positive. Now, imagine I gave you a curve that looked like this. And can we pretend that I'm really good at drawing the sine function, which is what that's meant to be? If I asked you to get the area under the curve from 0 to 2 pi of the sine function, I know the answer is 0. Now you might say, well, it definitely has area, and I'm not arguing, it does have an area, but the area under the curve is not the same thing as the physical positive area that you talk about when you normally think of it in the usual way humans think about areas. Anybody want to tell me, thank you, Joy, for telling me it was 90, just noticed you typed that in. Anybody want to explain why the answer to that is 0, even although I don't know what this piece is, and I don't know exactly what that space is, I still know that the whole thing is 0. Why? Any suggestions? Why is this area going to be 0? This area under the curve going to be 0? Okay. That piece and that piece are identical in shape, aren't they? isn't that piece the same size and shape as that piece? Which means that their areas are the same. That piece is going to be a positive number, and that piece is going to be the exact same amount, but a negative number. And when you combine a 5 and a minus, or a 2 and a minus 2, you eventually get 0. So that is the argument. So let's move on. Suppose I would like to find the exact value for the integral from -1 to 2 of 2x plus 1 dx. Now it's an exact value. So what I would do is I would sketch this function. Now I know it's a straight line, so really I just need to know where it is when it starts at -1 and what it is when it finishes. Right, if you plug -1 into here, you get -1, so it starts here. And if you plug 2 in here, you get 1, 2, 3, 4, 5, you get up here. And that's what my shape looks like. Okay, now I happen to know that that guy there is 1. So I guess I should draw my pictures much more neatly. So I'm going to have another shot at this. Here's 1, here's 2, here's 3, here's 4, here's 5. Here is -1. There's -1. Here is 1, here is 2. And it passes there, and it passes there, and finishes something like that. So that's what the straight line looks like. Now, since I want the integral from -1 to 2, I apologize. There we go. Since we want the answer from -1 to 2, we need to realize that there's a little negative piece down here, and then there's a big positive piece here. So I need to split this into 2 distinct areas. So we've got our curve, and it looks something like this. And there's a guy here, and then there's a different guy up here. And I know that's 5, I know that's -1. I don't know that position yet. So let's find out where that is. For the straight line, y equals 2x plus 1, it crosses the x-axis when the y coordinate is 1. So that guy there is -1/2. So yet again, another one of my pictures. This time I don't need to worry about doing it to scale. We have -1 to -1/2, and we have our line going like this. And then we have the rest of the line, which finishes up here. And the reason I need to do that is this green guy is positive, and this little guy here is negative. So let's call this guy A. Let's call this big piece here B. A is a triangle. Its width is half a unit. That's the distance from here to here. And its depth or height, whatever you want to call it, is 1. So it's 1/2 of base times height. And it ends up being 1/4. But I know it's below the x-axis. So it's -1/4. B, on the other hand, is also a triangle. The distance from there to there is 5.5. So it's 1/2, 5.5 times, and the height, which we got earlier, was 5. And so this one gives me 55 quarters, and it's positive. Why is it positive? It's above the x-axis. So the exact value for the integral from -1 to 2 of 2x plus 1 dx is this guy combined with this guy, which gives me, I believe, positive 54 quarters, which simplifies down to 27 halves. So the area of a straight line is almost always going to involve triangles. Sometimes one piece of triangle is below the x-axis and the other's above. If you're lucky, they're all above the x-axis, but triangles and rectangles is what you're going to have to deal with. Now, the third situation is shapes with pieces of circles in them. So the one I'm going to pick is a version of equation 3. And we're going to find the integral from -9 to 0 of 4 plus square root of 81 take away x squared dx. Now that's a pretty awkward function to try and visualize. So what I'm going to do is I'm going to go and use Desmos to sketch it, rather than me trying to figure out what it looks like by hand, which would probably not be very successful. Okay, so I'm ready. So let's see how that works on Desmos. Right, here's Desmos. And the curve was y equals 4 plus square root of 81 take away x squared. If you look here, I might have to shrink this a little bit. There we go. Can you see it's basically half a circle, and that it starts at -9 and it finishes at +9. But we are only interested in the integral from this side to here. So this is the piece that I want to find the area under the curve. So now I've got that, I'm going to do a little primitive version of it on paper. And we're going to work with that. So let's see what we have. Put a little invisible dotted line around here and drop some lines down to the bottom. Now, this guy here is -9 and this is 0. So the area under the curve is all of this shape here and this piece here as well. And I'll call this top bit P, and I'll call this bit here A. So the area under the curve is this total area here, right? A is basically a rectangle, 9 units by 4. So it would have an area of 36. This little piece here is a quarter of a triangle, a quarter of a circle. So it's 1/4 pi r squared. It's 1/4 pi times the radius squared. Now, if you look really carefully, you can find out the radius. It's that distance there, it's that distance there, it's that distance there. They're all the same distance, they're all 9. So this guy is going to be 81/4 pi. And so the area under the curve, now, since we are being asked to find exact values, I don't go 81/4 multiplied by 3.14 or anything. I leave it exactly as 81/4. So our answer is 36 plus 81/4 pi. Is there any questions about that? Are we okay? Just checking something. If you get what you expect to get. There. Now, just to convince you, which is what I was doing a moment ago, that we have in fact found the right answer. Can you see it here? 36 plus 81/4 pi. That's what we expect you to write down when you give your answer inside WebAssembly. So there's one next one-off question that we haven't looked at, and then we'll finish. We'll get started today at least, and we'll finish Riemann sums as soon as we can. You can do some combinations of areas, also called integrals, right? Suppose you are told that the area under a curve from 1 to 7 of this function was exactly 8.2, and that the integral from 5 to 7, right, the area under the curve from 5 to 7 of this function was 5.6. You could use it to find the area under the curve from 1 to 5. I know the area from 1 to 7. I know the area from 5 to 7. How would I find it? How would I find the area from 1 to 5? It's not a trick question, actually. It's pretty straightforward. How would I find the area from 1 to 5 using just these two numbers? Okay, I'd start with that one. There's a clue. So I would start with 8.2. Then what would I do? Ah, we have a channel. Correct. You would take away 5.6. And the answer is what? 2.6, I believe. So we have essentially covered those two guys, right? Now we're going to have to deal with the dreaded Riemann sums. First thing I'm going to get you used to, or even go there, is sigma notation, because it gets used a lot. Sigma notation, you can put in I equals 1 to 5 with I squared. There's an example of sigma notation. What sigma notation allows us to do is it gives us a concise way of writing down a calculation involving a whole load of things being added. So in this case, we would look at it like this. We're going to use a variable called I, sometimes called the counting variable. It's going to start at 1 and it's going to finish at 5. And we're going to add the values of I squared, with I being 1 and finishing at 5. So that would be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. Now, one of the great advantages in Riemann sums is that you can use it to represent adding up an infinite number of things, which is kind of hard to do any other way. So this would say, use your counting variable I, starting at 1 and just keep going forever, and add up whatever 1 over I cubed would be. So the first time it would be 1 over 1 cubed, plus 1 over 2 cubed, plus 1 over 3 cubed, forever. So sigma notation is a very convenient way of writing down a whole load of things being added. And we tend to use a variable I, but it can be K, it can be N, it can actually any letter you like, but I is a good letter, so I'm sticking to I. I'm now going to give you some truisms. These are just things that are true. I equals 1 to N, right, of the number 1. It's a very simple addition. We're going to start at I equals 1 and use 1 plus 1 plus 1, finish at 1, and we're going to have altogether N terms. And so this guy will add up to N. Now we're going to do I equals 1 to N of I. So that would be 1 plus 2 plus 3, and we'd finish what at N, and it'd still be N terms here. And I believe it was Leibniz, a German mathematician, discovered that all of these numbers from 1 to 2 to N, whatever N is, they add up to N over 2, N plus 1. So if you went and said, what would I equals 1 to 100 be, right? And you didn't want to have to go 1, add 2, add 3, add 99, add 100. According to this, it would be 100 times 100 plus 1 divided by 2, which is basically whatever 50 times 101 is, 5,050. And the next one is I equals 1 to N of I squared. And what we discovered with this one is that it would be 1 squared, so that's 1, plus 2 squared, which is 4, plus 3 squared, that is 9, and finish at N squared. And this one is N over 6, N plus 1, brackets 2N plus 1. I didn't do that very neat, so I'll do it down here. N over 6, N plus 1, 2N plus 1. Now these guys are going to get used. We're going to use these very special Riemann sums to find the exact value for the area under any curve, at least any relatively simple curve. And this is going to allow us to get the exact value using sigma notation, using Riemann sums. It's just another name for them. So I only have time today to do one of these Riemann sums. So imagine I have a function x squared, and I would like to find the exact value for the area from 0 to 2. I'll make it 3. The area from 0 to 3 of x squared dx. And I want to get the exact value. So I can't do Riemann, so I can't do trapezium 40. It would be a really good answer, be really accurate. I could maybe even have a guess at what the exact value is, but it would only be a guess. We are going to do Riemann sums on this process. So first thing I'm going to do is visualize what's going on. if you imagine what f of x equals x squared looks like, and you place that point at 3 and you place this point at 0, that's the guy that we're trying to find the area of, right? This base here. It's quite clearly positive, but that's not a big issue, even if it wasn't. Now, we approach the question as if we were going to do R8 or R10. We're just going to do Rn. So that means we would split this into n strips. Now, the width of the strip is b take away a over n. So it's 3 take away 0 over n, which is 3 over n. So that's our delta x. That's how wide our strips are. Now, normally that would be 8 or 4 or 22, and it'd be a number that you would use, but here is going to be n. That's fine. Now, when we did our usual table, x0, x1, x2, x3, and so on, xi, a general one in our table, would be a plus delta xi. So if you wanted to know what a random guy xi would be, you would simply start at a, in this case 0, and just add 1, 2, 3, I delta x's, which is what that is saying. Since in this case a is 0 and delta x is 3 over n, we now have xi, and it's, I guess, that guy. So start putting circles around important pieces. That guy's important, and that guy's important. Now, if I was going to find R8 or R4 or Rn, it would be adding up a whole load of rectangles, and it would be I equals, starting at 1 and finishing at n, the value of the function at xi times delta x. That would be the width of a rectangle, that would be the height of the rectangle. This would now become I equals 1 to n, the value of the function at 3i over n, times delta x, which is 3 over n. So this would become I equals 1 to n. Well, the function is x squared, so this is essentially my x. So I get x squared times 3 over n. This gives me 9i squared over n squared times 3 over n, which with a little bit of tidying up gets me 27i squared over n cubed. So essentially you can multiply things together and combine them. Now the next piece I'm going to do is allowed when you have sigmas. And what that says is that anything that's inside here, that's inside, if it doesn't have an I in it, you can remove it and bring it outside. So I can do 27 over n cubed I squared. And basically all I'm saying is add up all these I squareds and multiply it by that. It is the same thing as adding up all of these guys anyway, but this is easier to do. Why is it easier to do? Because we already know what one of those guys is equal to. Do you remember the sigma I squared was this mess? Let's use it. It's 27 over n cubed times n upon 6, n plus 1, 2n plus 1. Now I can do a bit of cancelling. An n can cancel with an n, a 6 can cancel with part of that guy. So what do I get? I get a 9 left. I get 3. I get 2 n squared left. I get an n plus 1. And finally, I get a 2n plus 1. And then I'm going to multiply all this out, which is 2n squared plus 3n plus 1 all over 2n squared, which gives me 18n squared, 27n plus 1 all over 2n squared. Almost finished. So if I use the right side of my strip and I use it n times, I will end up with this is my answer. So if I use 10, just put 10 in here and that would be my answer. If I used 1,000,000 strips, just put n as 1,000,000 in here and we would get our right answer. But since I want to get the exact area under the curve, right? The exact area, which in our case is integral from 0 to 3 of x squared dx. I don't want 5 strips or 10 strips. I want to find what the answer would be if I used an infinite number of strips. So we now need to do, to finish this question, is to find out what this Riemann sum is equal to when n goes to infinity. Now you have done limits before in Calc 1. In a limit situation like this, there are 2 methods, both work. One is L'Hopital's rule, and the other is divide the top and bottom by n squared rule. Anybody got a preference for which one of those 2 methods you want me to use to solve this limit? And someone has a choice, so let's see what she wants, or he wants. Okay, L'Hopital gets the job. Now, according to L'Hopital's rule, if the fraction that you're trying to find the limit of is undefined, that means 0 or 0 on the top and bottom, or infinity on top and bottom, as is in this case, then you can use it. So you put a little L for L'Hopital, you tell people that's what you're doing, and you do the limit as n tends to infinity, and you differentiate that, and you get 36n, and you differentiate that, and you get 27, and you differentiate that guy, and you get 4n. And then you try and put infinity in, and it's still in determinant form, and that's not uncommon with L'Hopital, so you just do L'Hopital. And you differentiate the top, and you get 36, and you differentiate the bottom, you get 4, and there you go. The exact value for that guy is 9. 9. Well, I just have time to prove it. I'm going to nip over to, there we go. Going to nip over here, and I'm going to go y equals, I'm going to put in x squared. Going to do the window from, I believe we chose 0 to 3. I'm going to go second calc, choice number 7. It's basically the same picture I had. Lower limit 0, upper limit 3. And do you see the answer is exactly 9? That means that we now have the power to find the exact value of an area under a curve using only the right sides, the RNs. But in order to do that, it's an awful lot of work. But at least we now know how to do it. Once we've done a few of these, we will then say, I want a shortcut, and we'll tell you how it works. Will you put your last name down for the